Hello. In this video, we study eigenvalues and eigenvectors. Before we move to detail, I would like to explain why we need eigenvalues and eigenvectors. In the previous video, we studied similarity of two matrices. We say that two matrices A and B are similar if there exists a matrix P which is invertible, such that A is equal to P to negative 1, B, and P. And we say that actually A and B in this case are two representations of a linear transformation in different basics. So that means they should have something common, right? They should have something invariant. If we change basics, some invariants are still there. Okay, so that is the main purpose of this lecture. They are eigenvalues. Make sense? So eigenvalues are invariants of a linear transformation. So whatever, if you change matrix in here, no problem. They are the same. Okay, so let's talk about the definition of eigenvalues. Suppose that you have some matrix A, let's say square, okay, a scalar lambda is an eigenvalues of A if there exists a non-zero vector x such that ax equal to lambda x. Okay, and in this situation, x is called an eigenvector of A corresponding to lambda, and x is an eigenvector of A corresponding to lambda. Okay, so you know the definition is pretty easy. Makes sense? Basically, in order to find eigenvalues and eigenvector, we have to work with this system, right? Ax equal to lambda x. For example, if you have some matrix A, 2, 0, 0, and negative 1, and you want to find eigenvalues and eigenvectors of this matrix, right? So basically, I have to consider the following one. Ax equal to lambda x, right? Since A is linear, from this inequality, I have Ax minus lambda x equal to 0, right? Or A minus lambda x equal to 0. So this system is equal to 0, right? So the matrix A minus lambda, so this system has non-trivial solution because we suppose that x is non-zero. That makes sense? So this system has non-trivial solution. That means the matrix A minus lambda I, lambda means lambda I, right? In this case, we have lambda 2, is singular. That means not invertible, right? So this matrix is not invertible, is equivalent to that the determinant of this guy is 0. And we use this equation to find lambda. Make sense? Let's do that. So I have to find A minus lambda I 2, right? I have 2, 0, 0, negative 1 in here, minus lambda, 0, 0, lambda, right? And then I have to take the determinant of this. The inside, I have 2 minus lambda, 0, 0, negative 1 minus lambda. And determinant of this matrix is just, product 2 minus lambda and negative 1 minus lambda. And I set this equal to 0, right? From here, we get lambda equal to 2 or lambda equal to negative 1. So this matrix has 2 eigenvalues, okay? For each eigenvalues, we still need to find the corresponding eigenvector, okay? So let's say, let's pick lambda equal to 2. And so I need to find x such that Ax equal to 2x. Is it correct? Or basically, if I use this system right away, right here, and I just plug 2 into the matrix, so I have A minus 2 identity x equal to 0. Make sense? I need to solve this system. All right, so if I solve this system, I have 2 minus 2, 0, 0, negative 1 minus 2. And this is homogeneous system, okay? The first row is just 0, 0, 0. Second row is negative 3, 0 in here. So this column is free, right? So we have one free variable. And this is, let's say, x2 equal to 0. The general solution of this system is x1 and 0, or x1, 1, 0. So from here, I say, yes, this guy is eigenvectors corresponding to lambda equal to 2. Make sense? And then for lambda equal to negative 1, we do almost the same. So we write the matrix is 2, 0, 0, negative 1, minus negative 1, 0, 0, negative 1. Because negative 1 multiplied with the identity. Makes sense? And you have to solve. Let's calculate this matrix first. So I have 2 minus 1 minus plus 1, 0, 0. Here should be 0, okay? And that is just 3. So if you have a homogeneous system, 3, 0, 0, 0, in here 0, 0, you solve this, this should be x1 equal to 0, and here x2 is 3, right? So you have the solution 0, x2, or x2, 0, 1. This vector is the eigenvector corresponding to lambda equal to negative 1. Make sense? That's how we can find, eigenvalues and eigenvectors. So basically, if you want to find eigenvalues, you have to solve this equation. The determinant of A minus lambda I n in this case, right? In general case, equal to 0. So you have to subtract 2 matrices and then find the determinant and set it equal to 0. Because that matrix is singular, right? And because of this system has non-trivial solution. Make sense? All right, let's move to the next example with 3 by 3 matrix. Suppose now I have some matrix A equal to 1, negative 2, 1, 0, 0, 0, 0, 1, 1, okay? And they ask us to find eigenvalues and eigenvectors. We do almost the same, but now I will do that very, very shortly. I will not write in detail. Okay, I will find a minus lambda I3 equal to 1 minus lambda negative 2 and 1, 0 minus lambda 0, 0, 1, 1 minus lambda. So look at this. Basically, I just pick all entries on the main diagonal of A, right? And subtract by lambda. You see that? It's pretty easy. All the entries are still the same, right? And then I will calculate the determinant, A minus lambda I3. So I need to find the determinant of this matrix. We have two zeros right here, which is good. So the determinant is equal to 1 minus lambda times determinant of negative lambda 0, 1, 1 minus lambda. And that is 1 minus lambda times negative lambda times 1 minus lambda, which is good. And that is just negative lambda 1 minus lambda square, right? And you set this equal to 0. From here you get lambda equal to 0 or lambda equal to 1. Okay? Here I want to mention one thing. The number 2 right here is called the multiplicity of eigenvalues lambda equal to 1. Multiplicity. Okay, why? Because if you write in this form, see 1 minus lambda times 1 minus lambda, so you have 2 times, right? But they are equal, so that is multiplicity of that eigenvector value. Make sense? Okay, we figured out the matrix has 2 eigenvalues. Now let's find corresponding eigenvectors. For lambda equal to 0, I plug lambda into this matrix directly. So I have the same one, just 1, negative 2, 1, 0, 0, 0, 0, 1, and 1. And I need to solve the homogeneous system, right? To find all eigenvectors corresponding to lambda equal to 0. All right, so we have the second row, 0, 0, 0, which is perfect. Now I multiply the third row by 2 and add to the first. I have 1, 0, 3, here 0, 0. I don't write the second row, and here is 0, 1, 1, right? That is the reduced row echelon form. From here, we can see, yeah, actually x3 is free. And x1 equal to negative 3x3, x2 equal to negative x3. The general solution looks like this. Negative 3x3, negative x3, and x3. You take x3 out, you get x3, negative 3, negative 1, and 1. So this is the main eigenvector. Of course, any vector of this form will be the eigenvector. Make sense? Actually, we know this is a subspace, right? Subspace. Because that is the solution set of homogeneous system. So there should be a subspace. And this subspace is corresponding to lambda equal to 0. You see? Because, we are working with lambda equal to 0, right? And we need to find eigenvectors. And all eigenvectors of this form will form a subspace, which is called eigenspace. That eigenspace corresponds to eigenvalue lambda equal to 0. Okay? All right, so let's move to lambda equal to 1. Again, we plug 1 into the following form, into this form, right? So I have the following one. A minus 1 lambda equal to 0, negative 2, 1, 0, negative 1, 0, 0, 0, no, 0, 0, 1, and 0. Okay, and we need to solve the system 0, negative 2, 1, 0, negative 1, 0, 0, 1, 0, and 0, 0, 0 in here to find eigenvectors. The second and the third are scalar multiple, so I just ignore one. I multiply the second with negative 2, add to the first. I get 0, 0 right here, 1, 0, 0. Here I can write just 1, 0, 0. Okay, here I have 0, 0, 0, 0. Okay, so from here we see, yes, actually this guy is free, right? X1. X2 equal to X3 equal to 0. Because when you set all these equal to 0, X2 is 0. You set this equal to 0, X3 equal to 0. So the general solution looks like this. X1, 0, 0. Or X1, 1, 0, 0. Vectors of this form are eigenvectors corresponding to lambda equal to 1. And again, this is a subspace, right? And this is the eigenspace corresponding to lambda equal to 1. Okay, so in this example, we learn how to find eigenvalues, eigenvectors, and eigenspace. Makes sense? The interesting is this. Given that the multiplicity of lambda is 2, right? You see? Multiplicity of lambda is 2. But corresponding to lambda, the eigenspace has dimension only 1. You see that? The dimension of the eigenspace is not always the same with the multiplicity of that eigenvalue. Don't forget that. Okay? At the beginning, we said that matrices are representations of linear transformations, right? And two matrices are similar if they represent the same linear transformation. Now we already know how to find eigenvalues, eigenvectors, and eigenspace of a matrix. So basically, those things are still good, are still well defined for linear transformations. Okay, so if you have some linear transformation, like from V to V, so the matrix should be square, right? The AT square. Okay. Then, you know, all eigenvalues of AT are said to be eigenvalues of T. All eigenvectors of AT are said to be eigenvectors of T, right? And of course, eigenspace also. So, you know, this is okay to talk about eigenvalues, eigenvectors, and eigenspace for linear transformation, okay? Let's consider the following example. Suppose that you have some linear map, linear transformation from R3 to R3, and the representation matrix in the standard basics is 1, 3, 0, 3, 1, 0, and 0, 0, negative 2. Okay, now we need to find all eigenvalues and eigenvectors of this matrix A. Okay, and then we will talk about, we need to find the matrix P such that A is similar to some diagonal matrix. Okay, we will talk about that. All right, so let's find eigenvalues, eigenvectors. First, I need to solve A minus lambda I determinant equal to 0. That is 1 minus lambda, 3, 0, 3, 1 minus lambda, 0, 0, 0, negative 2 minus lambda, right? we are good because we have 2 zeros in here and 2 zeros in here. So this is equal to -2 minus lambda times determinant 1 minus lambda, 3, 3, 1 minus lambda, right? And this is equal to -2 minus lambda times 1 minus lambda square minus 9, right? We can factor this out. We have -2 minus lambda, 1 minus lambda minus 3 times 1 minus lambda plus 3. Here we use a squared minus b squared equal to a minus b times a plus b, okay? So from here you get lambda equal to -2. From here you get lambda equal to, again, -2, interesting. And here you get lambda equal to 2. No, equal to 4, right? So this matrix has two eigenvalues, -2 and 4, all right? For -2 and 4, we can find eigenvectors. Let's say for -2. By the way, -2 has multiplicity equal to 2, okay? Lambda equal to -2. We can solve the following system. We have 1 minus -2, 3, 0, 3, 1 minus -2, 0, 0, 0, and 0. This is equal to 0, 0, 0. And this is 3, 3, 0, here 0, 3, 3, 0, 0, 0, 0, 0, 0. So basically this system is equivalent to one equation, right? Let's pick the first one. So I have x1 plus x2 equal to 0. From here I get x1 equal to -x2. And of course, you can see this. Actually, we have x2 and x3 right here. They are free variables, right? They are free variables. So I can write the general solution. Looks like this. -x2, x2, and x3. And if you separate x2 and x3, you get x2, -1, 1, 0, plus x3, 0, 0, 1. So all vectors of this form are eigenvectors of lambda equal to 2. And the eigenspace has dimension equal to 2. You see that? Because, these two vectors will form a basics. Agree? So, that is the difference between this problem and the previous one. In the previous one, you have lambda equal to 1 with multiplicity equal to 2, right? But the eigenspace has dimension equal to 1. In this case, lambda equal to -2 has multiplicity equal to 2. But the dimension of the eigenspace is 2. Okay? So that is big difference. Let's move to lambda equal to 4. Again, I plug 4 into this formula and solve the homogeneous system. So I have 1 minus 4, 3, 0, 0 in here, 3, 1 minus 4, 0, 0 in here. I have 0, 0, -2 minus 4, 0. Okay? So this is equivalent to -3, 3, 0, 0, 3, -3, 0, 0, 0, 0, -6, 0 in here. The first and the second are scalar multiples, so we can ignore one. I just write two matrix in here. This is similar to two rows in here. It's 1, -1, 0, 0, 0, 0, 1, and 0. I divide the third row by -6. Okay, so this is the row echelon form, and we see that x2 is free variable, From here I get x3 equal to 0, right? Because of this. From the first equation I have x1 equal to x2. So the general solution looks like this. x2, x2, and 0. Or x2, 1, 1, 0. This is the eigenspace corresponding to lambda equal to 4. And this eigenspace has dimension equal to 1. Okay, let me mention this. The dim of eigenspace equal to 1. You have 1 right here, you have 2 right here, the sum gives you 3, right? And that is the whole dimension of the space. Makes sense? This is very important. This is equal to the dimension of the whole space, R3. Okay? Alright. Now, we already have 3 representations of eigenspace. Actually, we have, basic vectors in here, right? That's what I want to say. The first vector is negative 1, 1, 0 right here. The second one is 0, 0, 1. And the last one is 1, 1, 0. Okay? So, I just want to verify one thing. These vectors form a basics. And we need to find the representation of our linear transformation in these basics. Make sense? And we see there's something interesting. All right, so let me point out in here. Negative 1, 1, and 0. 0, 0, 1, and 1, 1, 0 form a basics for R3. And they are eigenvectors of our matrix. Okay, now let's form a matrix P, which is equal to negative 1, 1, 0. I write those vectors in the column form. 0, 0, 1, and here 1, 1, 0. And let's verify that actually the AT 1, 3, 0, 3, 1, 0, 0, 0, negative 2 is equal to P2 negative 1. The diagonal matrix will be negative 2, yes, negative 2, negative 2, and 4, right? The last one is 4, yes. 0, 0, 0, 0, 0, 0, and here P. If we can verify this, that means we already found the matrix P that diagonalize our matrix. Or we already found the matrix negative 2, 0, 0, 0, negative 2, 0, 0, and 4. This is another representation of our linear transformation. And this matrix has diagonal form. Don't forget that. This is very important for computation because we know that, working with diagonal matrices is always easier. Make sense? So I want to suggest you to check this identity, okay, as an homework. Before we finish this lecture, I would like to mention one more thing. That is about multiplicity and dimensions in here, right? So in the previous example right here, we know that the multiplicity of lambda 1 is 2, right? And the multiplicity of 0 is 1. So we have 1 plus 2 is 3. But at the same time, the eigenspace corresponding to lambda has dimension 1, and the eigenspace corresponding to lambda equal to 1 has dimension also 1. So the total of dimension is 1 plus 1 is 2. You see? So that 2 is not 3, of course. They are different. Make sense? And I bet if you use the same logic of the example we just saw, right? If you write in this form, so you want to form a matrix P, right? A matrix P. So you take the eigenvectors. First one is -3, -1, and 1, right? The second vector is 1, 0, 0. So what is the third column? It should be 1, 0, 0, right? There's no other choice. But you know, this matrix is not invertible. So there's no way to write P to -1 diagonal NP. Make sense? So that is a big difference. In this situation, we say, yeah, the matrix A is not diagonalizable. Okay, we will study in detail in the next video. But please don't forget about it. When you find eigenvalues, eigenvectors, and dimensions of eigenspace, you need to compare the multiplicity of eigenvalues and the dimensions of eigenspaces. If the total give you two equal numbers, like in this example, 3 equal to the dimension of the whole space, you are good, right? That means you may find the matrix P satisfying this identity. Otherwise, you don't have that. Okay? So, I hope that, you know, we understand the idea of the problem. And one more time, I want to emphasize eigenvalues, eigenvectors, and eigenspace are invariants of a linear transformations, and matrices are representations of linear transformations. Don't forget that. All right? Thank you, and see you in the next video.